Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using Knime. In this chapter we're going to talk about low variance filtering. Another way of dealing with dimensional reduction is by measuring the variance. How much information does this column have? To limit the cases where a column, for example, has a constant value, the variance would be 0, and that column therefore would have no impact on your predictive model. So because it doesn't discriminate between different rows or groups of data. So we use the low variance filter node to calculate each column's variance and removes those columns below a given threshold. And much like you saw with missing values, what is that threshold? Well, we're going to provide the exact same example. This time we're going to use a low variance threshold instead. Now, a few notes about this. First, the variance can only be calculated for numerical columns, so the dimensional reduction technique only applies to numeric columns. Also, that the variance value depends on the column's numerical range. Therefore, data column ranges need to be normalized to make the variance values independent from the column domain range. So the concept is going to be very straightforward, implemented in Knime. We're going to normalize the numeric columns of the data set. We're going to remove the columns based on the data variance, and then we're going to denormalize the data back to its original state. So the basic structure is, first we use the normalizer node after we've read our data and normalize all column ranges to a value of 1 to 0. And then next we're going to use the low variance value filter node that calculates the column's variance and filters out those with a low variance. And then we're going to use the denormalizer to put it back into the range it originally was. Now, before I do that, I am still going to use the loop that we used in our example for missing values to find out what is the low variance filter value I should be using. So, as I was saying, with the example of missing values, the threshold selection is a critical topic. If you set it too aggressive, you lose information that's available in the model. And if you set it too low, you might not get the best reduction ratio. So we want to find that best value using the loop again. So one easy way I could do this if I like to make it part of the actual workflow is create a meta node that creates and determines the best value and passes that value back out. That way it would just be part of the workflow. But since I typically execute a model over and over and over again, I usually don't keep this. I'll usually run that meta node a single time. Once I know what the best threshold is, I'll retain it from there. Alright, to apply the low variance filter, we're going to use almost the exact same technique that you saw using the missing values. We're going to loop through the parameter trying to find the value that produces the best result. So to begin with, I do the same thing I did before, which is I partition my sample. 80% is going to be for training the data set, and then 20% for testing the model after it's complete. I apply missing values by setting numerics to 0 and string to unknown, just as I did before, and I apply that model to the partition data as well. So both data sets now feed into the same basic loop. So let's go ahead and look at this. And as you can see, it's the same thing. It's a parameter optimization loop. And within this loop, I'm going to start the parameter from 0.01, and I'm going to stop it at 0.1, and I'm going to do a step of 0.01. So I'm going to loop through each one of these. And I'm going to split, again, my column. I'm going to keep the target so to make sure the target's never lost, and I'll reconcatenate the target at the end. So I'll filter the low variance columns based on the value of the current variable, the current iteration of the loop. So I'm just going to do that by normalizing the data, applying the low variance filter. So the normalization take a quick look. Okay? I'm normalizing on a min-max function from 0 to 1. And then using the low variance filter on all columns, but the parameter, the max variance, is controlled by the new parameter, the flow variable. And then I denormalize it back again using the same model that I normalized it with. So I've run it, and I've run this now. Then I create my balanced target column using equal size sampling again. And then again I run it through the bag of models and the predictive optimization, which determines which of these models produce the best result. So I'll take that answer and feed that back into my loop. So again, just like the last time, I'll see all the settings from 0.01 through 0.1. I can see that at 0.01 I'm getting the best, the most objective model is coming out at 0.601. So 0.01 is going to be my best parameter. That's what I'm going to pass out to the model. Now with that, just as I did last time, I turn that into a row variable, and then I run it through a column splitter. Again, I'm separating off the target column because that cannot be lost. And then I apply the model that I use for normalization and denormalization again. So I'm going to apply the normalizer, do the low variance filter, and then the denormalizer. And again, using the same threshold that was controlled by the variable again. So the upper variable is still controlled by the new parameter. And then finally, I reintroduce the target by appending the two of these back together again. So you'll see, and we're going to see for each of the coming dimensional reduction techniques, the same model kind of reappears over and over and over again. That completes this chapter of the class. Feel free to move on to the next chapter.